Guys, this is David. Today I want to talk about the concept of degree of freedom. First, let's start off by going through the definition of degree of freedom. It is the minimum number of variables required to describe the independent motion of the system. And I still remember when I first read this definition, I totally had no idea what this is talking about. And if you have the same problem too, don't worry because now I'm going to explain it to you with an example, which is a rigid body in a plane. In order to know how many degrees of freedom a rigid body in a plane has, let's first look at how many kinds of independent motion it can have. By now, you are probably already guessing that it can move vertically and horizontally in the plane, and that is correct. So now that means we have two kinds of independent motion. And in fact, one more kind of independent motion that it can have is rotation about the z-axis, which is shooting off the plane. So now we know that for a rigid body in a plane, there are three kinds of independent motion, and we need at least three variables, x, y, and theta, to describe all these independent motion, which by definition shows that a rigid body in a plane has 3 degrees of freedom. However, say now we have a system with two rigid bodies that are jointed together. How many degrees of freedom does the system have? In order to answer this question, we will have to focus on kinematic constraints. Kinematic constraints, by definition, are constraints between rigid bodies that result in reducing the degree of freedom of a system. In planar mechanisms, there are two commonly seen kinematic constraints. The first one is revolution joint, or R joint in short. Usually, R joint is represented as the little circle over here. What revolution joint basically does is that it will stop the rigid body from moving freely in the vertical and horizontal direction, but it will still allow rotation, which results in reducing 2 degrees of freedom of the rigid body. This result can also be obtained from a mathematical point of view, since originally we need at least 3 variables to fully describe the motion of the rigid body. But now, since one end of the rigid body is constrained with the R joint, therefore, it means that the x and y coordinates can both be represented as functions of theta, which are shown here. And these two equations are what we call constraint equations. So now, the degree of freedom of the system reduces from 3 to 1. Now, let's look at the second type of joint, the translation joint, or T-joint in short. What a translation joint does is that it restricts the motion of a body to pure translation relative to another body. For example, here's a slide translating on the ground, and in other words, the slide and the ground are connected by a translation joint. As you can imagine, the slide can only move freely in a horizontal direction and cannot have translation in a vertical direction, nor rotation with respect to the ground, which results in reducing 2 degrees of freedom of the slide. And again, this result can be obtained from a mathematical point of view, since we know that the slide is translating on a plane with height equals to yc, and that the slide cannot rotate with respect to the ground. And these two properties can be described with the constraint equations shown here. Therefore, the degree of freedom of the system reduces from 3 to 1. From the previous revolution and translation joint examples, we see that both of the systems are now a 1 degree of freedom system, or a 1DOF system in short. And what is so special about 1DOF system? The importance of 1DOF system is that given any one of the variables used to describe the motion of the system, then all the other variables can be determined. This may seem to be confusing at first, but now let's demonstrate it with the revolution joint example. Here is the example we have seen in revolution joint, and as we have explained, this is a 1DOF system. In order to prove that it is possible to determine all other variables used to describe the motion of the system after any one of the variables is given for a 1DOF system, let's now assume that the x-coordinate of the point on the rigid body over here, is given, and recall the fact that x equals to 0.5L cosine theta plus xc, where xc is a fixed and known value. With this information, we will be able to determine theta by the equation theta equals to cosine inverse x minus xc divided by 0.5L. And after theta is determined, the y-coordinate of the point can then be determined by the equation y equals to 0.5L sine theta plus yc, where yc is a known and fixed value as xc, which proves that we are able to solve for all other variables y and theta once x is given. Analogously, we can do the same thing once y is given and determine theta by the equation theta equals to sine inverse y minus yc divided by 0.5L. And after theta is determined, we can then determine x by the equation x equals to 0.5L cosine theta plus xc, which again proves that we are able to solve for all other variables x and theta once y is given. Last, assume that theta is given, then both x and y can then be directly determined by the equation x equals to 0.5L cosine theta plus xc and y equals to 0.5L sine theta plus yc. Now, we have proved the fact that for a OneDOF system, once a variable used to describe the motion of the system is given, then all the other variables can be determined. And the other reason why OneDOF system is worth mentioned is because most planar mechanisms are OneDOF system, such as crank and rocker mechanism and slider crank mechanism. You may be wondering why these mechanisms are OneDOF system. Therefore, now let's take a look at the crank and rocker mechanism first. For a crank and rocker mechanism, there will be 4 bars and 4 revolution joints in total. And recall the fact that each bar has 3 degrees of freedom under the assumption that the bars are rigid body. And each revolution joint will reduce 2 degrees of freedom of the system. And also note that the bar down here, or sometimes we just call it ground, cannot move at all. Therefore, the total degree of freedom of the system is 3 times 4 minus 1 minus 4 times 2 equals to 1. Next, for a slider crank mechanism, there will be 3 bars and a slide and 3 revolution joints and 1 translation joint in total. And recall the fact that each translation joint will reduce 2 degrees of freedom of the system, and the ground doesn't move at all. Therefore, the total degree of freedom of the system is again 3 times 4 minus 1 minus 4 times 2 equals to 1. Now we have proved that these 2 planar mechanisms are OneDOF system. And in the next video, we will show you how to perform kinematic analysis on these systems by deriving the constraint equations for these mechanisms.